So the first few days are going to be largely built around review of stuff that we sort of already know how to do, right? And built into that, we'll do some strategic stuff also. Okay, questions like this. Whenever it asks you to do something like choose the expression that is equivalent to, or choose the simplified expression, or something along those lines, you're not having to do anything hard. You're not having to solve an equation. All you're doing is you're picking which one of these options here is the same thing as this expression, just written in a different form. That's it. Okay? So mathematically, what would we do? Mathematically, we would have to do like PEMDAS, right? Where we would take this expression right here. We'll just do one of these. I'm not going to do them all. We would take one of these and we would go through PEMDAS to simplify this, to write it in its simplest form, right? And then we would see which of these other ones simplify to give us the same answer. Mathematically, algebraically, that's how we would do it, right? So if we followed PEMDAS, what would we get? Well, the first thing we'd have to do is we'd have to take that exponent and expand that out, right? So what is x, that code? So what is x plus 5 squared? That's a pattern we know, right? A plus b squared is what? No. A squared plus 2ab plus b squared, right? Or if you forget it, right? If you forget it, you can just multiply it out. But the thing I'll say this, I've said it probably 100 times, and I'll say it again. What you cannot do, if you're adding or subtracting, you can't just distribute the exponent. It does not work, it never will, right? It's harder to square something that's being added or subtracted than it is if it's being multiplied, right? There's more work to do. So our pattern would be a squared plus 2 times the product of a and b. Well, x times 5 is just 5x, times 2 is 10x. And then 5 squared, 25, right? Good. And then, so there's that part, right? So we're going to get x squared plus 10x plus 25, right? Now, what about this part over here? Okay, that's just a product. I'm just multiplying x plus 5 times x minus 1, right? I'm just going to distribute. So if I distribute that out, I'm going to distribute the x, and I'm going to get x squared minus 1x. If I distribute the 5, and then 5 times negative 1. Okay, but keep in mind that we still have this subtraction sign out front, right? So I've got minus that whole thing, right? Okay, so what do? Well, I want to just simplify this first of all. So I'm going to get x squared plus 10x plus 25 minus, and then if I simplify that, I can combine a couple of like terms, can't I? So I'm going to get x squared plus 4x minus 5, and now finally when I distribute the minus, what's that end up being? Good. Okay, and then so we get x squared plus 10x plus 25, and if I combine all the like terms, well, look what happens. The x squareds are going to cancel, right? And I'm going to get 10x minus 4x is 6x, 25 minus, oh, I didn't distribute that, did I? Oh, 25, sorry, 25 plus 5 is plus 30. And so there's my answer, right? So then all I would have to do is just go through the rest of these and see which of those equals that. Now, a lot of this is going to be process of elimination, though, isn't it? You can already see that if I do x plus 5 minus x plus 1, I'm not getting that, am I? I'm not going to get a 6x right away. You can see that, can't you? So we could just cross that off, right? How about here? I'm going to get 4 times x plus, who cares? It's not a 6x. It's already wrong, right? So we cross it off. That one looks hard, so let's do the bottom one. If I, seriously, I mean, that's how.
Yeah, I just want to hear you say it.
I mean, when I say hard, I mean, it's long. There's a lot of stuff to do there, right? So why don't we see if the bottom one works, because it's easy, and if it doesn't, if we cross it off, we're done, right? So on the bottom, if I distribute the x, I'm going to get an x squared plus some stuff times 2. It's already wrong. I don't have an x squared there, do I? Right? So it's already wrong. So we know it's C, right? Okay? You get the idea? Okay, now that's the algebraic way to do it. Okay? I got a better one for you, though. Okay? So let me take a picture of this. I want to save all this stuff for the notes.
So are you recording?
I am recording.
Stop that. Stop it. Stop it. You see, Jamie is perfect. Yeah. Oh, the font really is wrong.
Okay, so here is using algebra, right? Okay, but we can be pretty tricky about this. Okay, there's a great trick. This is the one I alluded to last week, right? Whenever you're doing stuff like this, where you're trying to compare expressions, all you have to do, this is the one where you can, if I know that this equals one of those possibilities, then the trick is if I pick a random value of x to plug in, it's going to be the one that gives me the same value back when I pick a random value of x, right? So what if we pick, just hypothetically, let's just pick 0, I mean, we could, we can, that's fine. 0 will work. Let's try 0. So what if I pick x equals 0? Then what do we get? Okay, so this guy's going to give us, if I pick x equals 0, I'm going to get 0 plus 5 is 0. Is 5. Squared is, okay, minus 0 plus 5 is 5, right? 0 minus 1 is, so 5 times negative 1 is negative 5, so I get 30 if I plug 0 in. Okay, let's try the others. So if I pick 0 here, I'm going to get 5 minus negative 1, not 30, right? So we cross it off. How about this guy? Okay, here, let me just, so you can see what, I'll just cross it out there. Okay, how about this one? If I plug in 0, I get 20, right?
You can say that's not 30.
So we cross it off, that's not 30, right? How about this guy? Now this is pretty easy. It looked really hard before, but if I'm just plugging in a value, it's pretty easy to evaluate. So if I pick this one, I'm going to get, out front, I'm going to get 0 plus 5 is 5 times 5 minus negative 1, right? Well, what's 5 minus negative 1? Okay, that's it, isn't it? Just to check, though, because it's possible, every once in a while, you're going to pick a value of x that's going to accidentally work on another one too, right? Every once in a while. So we should just check the bottom one and make sure. So if we plug it in on the bottom one, we get 2 times 5 is 10 times negative 1, negative 10. So we got it. How easy is that, right? It doesn't always work, but on the questions where you're trying to just compare to see equivalent expressions, or, you know, and there are a lot of those, that's a go-to. It's pretty quick and easy to do, okay? Okay, so here's an example of one where, you know, we can do this algebraically. Algebraically, this is right where we left off. right? This is difference of cube stuff. If we're trying to factor this thing, you know, we can write this as, this is the pattern that we looked at last week. We had 4 patterns. Sum of squares, which is not a pattern. Difference of squares, right? Just a quick review. So these were the patterns we learned. A squared plus b squared, remember, is just a squared plus b squared. There's no pattern. It doesn't factor ever, right? A squared minus b squared, we call that a difference. That's a sum. A difference is when you subtract. So difference of squares, remember what that one was?
A is a plus B, A is minus B.
Good. Okay, so there's a pattern we know. And then we know the cubes. We know like the sum of cubes and the difference of cubes are strongly related. They follow the same pattern, right? We know that sum or difference of cubes, I know that the terms are going to be a and b in the binomial, and a squared and b squared, and in the middle I'm going to get an a times b, right? But the trick was, remember, that whatever I have here shows up there, and then the next sign is going to be the opposite, and the last one is always plus. Remember that? Okay, so down here, we're going to get minus, oops, plus, and plus, right? And so we could use those patterns. We could use those patterns, and we could rewrite this thing as, if I'm starting off with 27 x cubed minus 729. Well, could I write that as a difference of cubes? Could I write it as something cubed minus something cubed? Yeah, I could. That would just be a 3x, right? And that's a big number, but that happens to be that 9 cubed. And so I could follow the same pattern, and it would work out to be exactly, if I follow that pattern, there it is. Okay. The other thing I could do with this is I could take my original equation up here, and I could factor out a greatest common factor right from the start. Okay, I could factor out a 27. If I factor out a 27, what I'm left behind with is x cubed minus 8. No, x cubed minus, 27. 27 times 27 is 729. That's right. Okay? And so I could break this up into 27 times x cubed minus 3 cubed, and that would give me this result. Okay? So algebraically, we can sure do it now. No big deal, we can. Okay? But okay. But once again, can you see a shortcut on this one?
Just
Plug in something, right? What if we plug in something like,
well, let's plug in 0.
we could try plugging in 0 again. Okay, you gotta be a little careful with 0 sometimes. It's such a simple number that it can trip you up, right? But that's okay. Look, what if we plug in 0? If we plug in 0, what do we get from this guy here, right? So that would equal negative 729. I'm going to agree, I'm going to get 27 times 0 cubed is just 0. So I get negative 729. Okay, so what about these guys? Well, if I plug in there, I'm going to get negative 9, right? 0 minus 9 times 0 plus 0, 81, right? And sure enough, that's negative 729. I multiply that out. Okay, what about here? I'm going to get 27 times negative 27 cubed, right? not even close. It's a huge number, way too big. So that one's a no. Okay. How about this guy? If I plug in 0, I'm gonna get negative 9 cubed. Okay. Well, that is negative 729. So that one's still in the running, right? And then how about down here? If I try this one, I'm going to get 27 times negative 3, right? 0 minus 3 times 0 plus 0 plus 9. And that also gives me negative 729. So it worked for 0, but now we'd want to check another number. Like what if we check something like, like 1, how about? Okay, so but we only have to check these guys, only the ones that succeeded. So if we check like x equals 1, then what would happen? Well, this one right here, if I check x equals 1, is going to give me 3 times 1 is 3, minus 9 is negative 6, times 9 plus 27, right? So that's 36 plus 81 is 117.
Yes.
Okay, and that's going to give me some big number. Somebody real quick, what is that? No, it's going to be negative 702. Okay, if I multiply that out, I get negative 702. Okay. That one's already out. What about this guy? If I plug in 1, I'm going to get 3 minus 9 is negative 6 cubed. Well, that's negative 216, right? And thank you. Okay. And then what about the bottom one? Right, if we try that one, if I plug in 1, I'm going to get this bottom one, I would get 27 times negative 2 times 1 plus 3 is 4 plus 9 is 13. So that's 27 times negative 26, and that would equal negative 702. We still haven't checked the top one. What about that one? Well, if I plug in 1, I'm going to get 27 times 1 is 27 minus 729 is negative 702. So it worked. So these two stayed solutions, whereas that one didn't work out because 0 accidentally worked. Okay, so the moral of the story is, yeah, in fact, 0 is probably the one on the test. That's the one that they assume you're going to try. So I would prefer. I mean, I would recommend you don't use it. Okay. Even though it's really, one's a pretty good one to use. Yeah.
Because they think you not to use this.
No, so they're not that tricky.
Reverse
They don't
psychology.
think we're that.
Reverse psychology.
Okay,
Reverse psychology, let's go.
Okay, now, so here's the deal. That took a little while to do, right? But that's still so much quicker than the alternative, right? So, but the moral there, I guess, also is just because it works with one number, you want to try a second number because you can get situations where it accidentally works with one, right? But the odds of it working for two separate numbers are spectacularly low. It puts you up there where it's a really good educated guess. If it works twice, then it's going to work. Okay? Question?
Do you know if any of those things works like on like standardized testing or like SAC stuff, or like you don't know, guess C?
No, that's a bad idea.
Bad idea.
No, if you don't, but what you should do, here's, on this one, I have to verify this and I'll find out. I don't think there's a penalty for guessing on this one. Okay, so you can always, I'll verify that, but I think you can always guess. But if you can eliminate at least one, then your odds go up substantially, right?
Yeah, that's how people.
So what do I do if I don't know something on the SAT?
You
On the
eliminate
SAT, I think they changed it. I think there's no penalty for guessing now on the SAT. I think statistically your odds are the same. I believe that's the way it is now. They changed it, I believe, but you'll want to check. Okay, next. So what about something like this? Okay, here's an example of one where they want you to verify each of these to see if each one of these statements is true or false. Okay, now we can do that. There's a lot of algebra here. And we could look at this and say, well, I mean, probably a lot of these we can immediately cancel out, right? Because we know that x plus 4 squared is x squared plus 8x plus 16. So we can see that that one automatically is a no. Right? That one we can eliminate right away. That's an easy one. Here's one where, let's see, we're going to get, if we try this one, if we expand that out, we're going to get 3x quantity, so 9x squared plus 2 times 3x times 9 is going to be plus 54x plus 81. Well, if I do all, I'm going to find out that one does work. If I go through the math on it. Okay, I would find out that it does. If I expand this out and then distribute a 9 through, whatever I get from that, I'll find out it works. So I can go through the algebra on this, but once again, what's the easy way to go with this one? Plug in a 1. Absolutely, plug in a 1. Okay, so, and you might even be able to quickly, is 0 a horrible idea? No, not really. But if you check 0, you can eliminate some, but then the ones that survive, you want to check with another one, right? So if we start off, the first run through, what if we pick x equals 0, just to get rid of some, right? If we pick x equals 0, what do we get for our result then? So, first time through, this one's going to give us the equation negative 5 times negative 5, right, is positive 25 equals 0 minus 25 is negative 25 squared. Not even close, right? So not equal, that one is out. If it doesn't work, at least we know it's done. We don't have to try it again, it's out. Okay, how about this one? Plug in 0. I get 16 equals 4 squared. So that works, right, so far. So far, it made the cut, but we want to check it with something else too. How about this one? Let's see, if I plug in 0, I get 9 squared, so 81 equals 9 times 9. So that one also makes the cut, right? Makes the cut. And then bottom one, if I plug in 0, I get 49 equals 49. So all those made the cut, but I eliminated one. So now if we pick x equals 1, let's see what happens. If I pick x equals 1, that one we already know is out. This one's going to give us 1 plus 16 is 17 equals 1 plus 4 is 5 squared, 25. That's not true. So it's out. Right? How about here? If I plug in 1, I'm going to get 3 times 1 is 3 plus 9 is 12 squared equals,
9 times 16.
yeah, so I get 9 times 1 plus 3 is 4 squared is 16. That's true. It works. So that one worked twice, so it's a yes, right? Bottom one. If I plug in 1, I get 1 plus 14 is 15, plus 49 is 64, equals 1 plus 7 is 8 squared. True. See what I'm saying?
So you could logically start out with 1 and so what?
You could. You could start out with 1 and then plug 0 in for your other one if you wanted. Yeah. The 0 is so easy to use for the ones that survive. Maybe it's easier to do that because you can eliminate more the first time through. Okay?
You just invented a theorem, that was it.
Yeah. There you go. So this is properties of exponents stuff, right? So I mean, once again, we can do these using properties of exponents. Let's just look at 2 of these just to get a quick review of our properties of exponents stuff. Right? So what about the top one? Yeah. Let me do this. I'm gonna. So if we're going to do this the long way, properties of exponents. Like what about this top guy here? So I get y to the x times y to the x. Well, if I multiply like bases, what do I do to the exponents?
Decrease the
Add. Multiply like bases, you add the exponents, right? So that's y to the x plus x. Well, is that y to the 2x? X plus x is what? 2x, yeah. So, yeah, that one we could, it's true, right? Okay, how about this guy down here? So I get 5 to the 3x. Is that equal to 3 to the 5x? Okay? Well, if I take, now think what this could be. If I take 5 to the 3x, that's the property that we get when we take a power to a power. If I take a power to a power, that's when I multiply the exponents, correct? So that's the same thing as saying 5 cubed to the x, right? How about over here? Well, this would be the same thing as saying 3 to the 5th to the x, okay? Well, that's 15. Actually, no, it's not. It's 5 cubed is 125. So 125 to the x, 3 to the 5th is 243. They're not equal, right? 125 to the x is not the same thing as 243 to the x. So that one is a no, okay? That's the algebra way, using properties of exponent stuff, okay? But can we be tricky? Yeah, we can, right? So this time I've got, in all three of these, I've only got one variable that's an x. In this one up here, I've got two variables, y's and x's. Okay, so that's okay. Let's just pick values for x and y and see what happens. Let's not pick 0 or 1 though, for stuff like this, because they're too symmetrical. Let's pick like 2 and 3, how about? Okay, so what if I pick something like, let's say y equals 3 and x equals 2, and see what happens. So this first equation is going to be 3 squared times 3 squared equals 3 to the 2 times 2 is 3 to the 4. That's true, right? That's a true statement. I get 9 times 9 equals 81. True. Okay, so that one worked. Okay, how about this guy? So I'm going to get 16 to the 2. Is that equal to 4 to the 2 times 2? Once again, that works. I get 256 equals 256 if I plug it in my little calculator, right? So, yes, that works. Okay. How about down here? I get 5 to the 2 times 3 is 6. Is that equal to 3 to the 10? No, it is not. If I try that, that works out to be, well, I'd find that that's a really big number. They're both pretty big numbers, but they're not going to be the same, right? They're not going to be the same. For one thing, I know it's not going to be the same, because if I multiply things like 3 to any power, am I ever going to get a 0 on the end of that? No. No, I don't think. Is that right? I don't think so. I don't think so, no. Okay, but I could just see what those are on my calculator, and they're clearly different, right? So that one is a no. And then how about this bottom one?
No, is it no?
Definitely a no, isn't it? 12 times 2 is clearly not equal to 4 to the 6, not even close, right? So that's a no. Okay? All right. Let's see if we can get through maybe just a couple more here. So this one, now I want to get to these. So these kind are, unfortunately, these are ones where the tricks don't work. Now you can check your answer with a trick, but these are ones where you literally do have to go through the math, right? Because you need to see when I do the math, and they really like these because you have to do the math on this. You're likely to see a couple of these. But you know your choices are from that box down there, so it does limit things a little bit, right? But this is one where we would have to take the original statement and we'd have to simplify it. Okay? But we're just following PEMDAS, no big deal. Okay? And so we'd end up with, let's FOIL this out first. So I'm going to get 3 times, if I distribute the 3x, what do I get?
6x.
Okay? 3x times 4.
12x.
Okay? 2 times 2x.
4x.
So I'll just line those up, right, because they're like terms. And then finally, 2 times 4 is plus 8, right? So I get 3 times 6x squared plus 16x plus 8. Now, if I distribute the 3, that's just going to be 3x squared plus 48x plus 24. So we got values that fit, right? Make sense? Okay? Okay, so we know that that would be a 3, and that would be a 24. So you could, if you got one like this where you were totally, just couldn't figure it out, that one you could, but what if it were harder? There is one other little trick you could try on this. Yep.
Is that, yeah, 3 times 6 is 3.
Oh, did I not?
Yeah.
Oh, it's 18. Whoops, 18. Sorry. Yep, let me go back. Well, there wasn't even a 3, was there? So we would have definitely found that. So it's 18, which makes this an 18. Okay. Okay? Make sense? Okay? All right. To check it, we could easily plug in like 1 and just see if it works, right? So, do we have time? This is the other one I wanted to do. So on this one, here's what I want to show you on this one. Just one little thing, right? So if I'm starting off with 4 times x plus 3 times 2x plus 2 over 12. Here's the one thing you can think about that makes this a lot easier. We only are going to multiply and divide in pairs, right? So what we could do, for example, is we could multiply out the whole top of this and just divide each term by 12.
You're going to ride slowly today.
Okay? Or,
If you go to Sherwood
make
and
things
Mackay,
easier,
you're going to ride slowly
4 over
today.
12 reduces to what? 1/3. So that becomes a 1 and that becomes a 3. And now look how easy the top is. If I just distribute the top out, I'm going to get x times 2x is 2x squared plus 2x, I just plus 6x plus 6 all divided by 3. Well, that's 2x squared plus 8x plus 6 all divided by 3. Just break it up. Instead of a common denominator, just break it up into parts. Right? And so I'm going to
Is
get
McFarland to the tennis office,
2/3
please?
x
Aiden
squared
McFarland to the tennis office.
plus 8/3 x plus 2. We got our answers, right? You see that?
Yeah.
Okay? All right, we'll pick it up tomorrow.
We had a 25-year high for measles outbreak in the United States.